is Josh Fuhrer, and I'm here today to present my Pecha Kucha on, you guessed it, some more math. This is kind of a stab in the dark, but I was thinking what I wanted to do this on, and I picked 19 math theorems that are near and dear to me, that I've used, that are useful, and hopefully you guys will see some use in there. The first one is the binomial theorem. Pretty much allows you to expand x plus y to the n. It's closed form summation. The coefficients used are the binomial coefficients, which some of you may know from Pascal's triangle. This whole identity was first seen by Blaise Pascal. Next is Cantor's theorem. I chose this not so much for what the theorem says, but the controversy surrounding it. Cantor's theorem involves the idea of an infinite set, which many mathematicians think is more theological and philosophical than it is mathematics. That's why I chose it. The central limit theorem unfortunately didn't show up, but if you've taken stat, you've probably seen it. It's a great way to convert discrete probabilities into continuous ones, and it gives us our bell curve, which we all know about because we're also concerned about averages and standard deviations here at Hopkins. The Euler's formula is actually one of my favorites. It popped up earlier in the semester when I was talking about cryptology, because it's used a lot in RSA, which is a cryptographic system, and it's quite a very concrete, and I think it's a beautiful theorem. Just me. And the phi of n, of course, is Euler's Todien's function. Fermat's last theorem is probably the most famous math theorem ever. Fermat conjectured it in 1637, and it was not until 1995 that it was actually proven. It is the Guinness Book of World Records' most difficult math problem. That's a fact. It's quite a doozy. Of course, again, the picture doesn't show up. The four-color theorem. Imagine the map of the United States. Each state is a node, and two nodes are connected if they share a border. The four-color theorem says that you need at most four colors to color any map. If you look at any map of the US, there will be four colors on it from the four-color theorem. Fundamental theorem of calculus, I'm sure you guys know this because everyone had to take Calc 1. It pretty much gives us a relation between an indefinite integral and its antiderivative. It pretty much just takes the area under a curve. Newton and Leibniz, who are kind of the two fathers of calculus, conjectured this and wrote it up. Gauss's theorem, once again, no picture, but I'm going to keep going here. One of the big three in vector calculus, it relates the flux of a vector field through a surface to the vector field inside the surface itself. Engineers use it a lot for things like water flow and stuff like that. Sweet. Another one, Goldbach's conjecture. What it says, if the slide worked, is that the sum of 1 over p minus 1 over all perfect powers converges to 1. I picked this not for the theorem, but because Goldbach also has an unsolved conjecture that says every even number is the sum of two primes. Unproven. If you can prove it, you'll make a lot of money. Green's theorem, also no picture. I'm sorry about that. This is the second of the big three in vector calculus. It relates the line integral around a simple closed curve to the double integral of a region surrounded by that curve. Green's theorem is kind of like no one likes Green's theorem. Hall's-Marr's theorem, to put it simply, there's n men and n women in a group. Women are picky, so they only have a certain amount of men that they want. A man will accept a woman if she likes him. Hall's-Marr's theorem says that under certain circumstances, everyone will go home happy. So that's Hall's-Marr's theorem. Lagrange's theorem says that for a group, the subgroup H, the amount of elements in that subgroup will always divide the group itself. It's actually, I picked this because it goes back to Euler's theorem that I like so much. Joseph Lagrange did not prove it. He conjectured it. It was proved by a BT, some other mathematician. Menger's theorem is a graph theory principle, but probably better used if you guys have ever looked at directed graphs, things like shipping. UPS would use something like this for looking at the minimum distance between two places that uses the least amount of energy or the least amount of gas, things like that. Pythagorean theorem. We all know Pythagorean theorem. I picked this more because I wanted to talk about Pythagoras. He was believed to be able to travel space and time. He was kind of a weird guy, and the Pythagoreans, his cult, he did have a cult following, very secretive weird things going on there. Quadratic reciprocity, of course, no picture, why not? Number theory topic. It's a way to look at quadratic equations, not the way we know them, but in a modular world. This was conjectured by Euler and Lagrange. The Lagrange symbol, if you look it up, just kind of simplifies the formula into a concrete form. Star of David theorem, I really wish there was a picture. It talks about the greatest common divisor of connected binomial coefficients, and the actual picture is a Star of David, proven in 1972 by H.W. Gould, who my guess was probably a Jew. Just because. Again, Stokes' theorem. Stokes' theorem is the granddaddy of them all in vector calculus. It is a pain in the butt to prove, trust me, but it really does the work when it needs to be done. Electromagnetism, for example, is able to relate the electric field to the magnetic field, which is something that physics 2 people really like to use. Taylor's theorem, if you've ever expanded a function to look at a specific point and approximate it, you've used Taylor's theorem. The more derivatives you use, the better your approximation. And named after Brooke Taylor, but proved by our friend Lagrange, which, in conclusion, brings me to Wilson's theorem. Spoken out, I guess, in English, it says that n minus 1 factorial is congruent to -1 mod n. It's used in testing numbers to see whether or not they're prime, and it was John Wilson who got named after, but you'll never guess who proved it, Lagrange. Thank you very much.